Carlo methods a few years ago, which is concerned with ways of approximating some Monte Carlo algorithm, and in particular Markov chain Monte Carlo algorithm, which will be the focus of my talk, but in an exact way. It turns out that these algorithms look like approximations, but that they are exact, hence the title. And so the talk will, I'm not going to present new material mostly in the talk. It will be more like an overview, and in some places not very precise, but hopefully not too wrong. So this is the plan of the talk. So first I will start talking about where in some ways it all started with the idea of approximating densities with unbiased estimators, and then I will move on to basically a generalization, which is that of approximating acceptance ratios in Markov chain Monte Carlo methods, and then I will talk briefly about whether it's really worth it to be exact, right? So I will start with exact marginal approximations or pseudo-marginal approximations. And what is the main idea in this scenario? Well, we are in the scenario where we want to sample from a distribution with density pi of x, but that density pi of x is very complicated, okay? It's not possible for various reasons to evaluate it pointwise, even up to normalizing constant. So this is what I will mean by intractable throughout the talk. But in some situations, for any value of x, it is possible to compute unbiased measurements of the density pi of x. So really I'm talking about measurements of the value of the density at any point in the state space of interest. And it may be that doing this is very cheap, in particular cheap in comparison even to evaluating the density. And in recent years, so maybe this novel should be between quotes, some MCMCI algorithms have been proposed that exploit exactly this scenario, and these algorithms have been designed to sample from pi of x. And the main idea is extremely simple. It consists of saying, well, whenever in my algorithm I need pi of x, the true value of the density, I'm going to just replace it with a noisy unbiased estimator wherever it is needed. So that's the starting point. The key point is that the resulting algorithms, and we will go through this in some detail at some point, basically these algorithms are of course perturbations of the algorithms we would have liked to implement, the idealized algorithm, which would use pi of x, but it turned out to be approximations that are in fact exact, okay, in the sense that it turns out that the algorithms are really doing what we want it to do, that is sample from pi of x, although pi of x is not used explicitly. And what I will attempt to do in this talk is to show some of generalization of these ideas and how they are interrelated. That's the aim of the talk, right? So first, a simple idea. So let's assume that we are in this framework where pi of x is a posterior distribution, for example. So it's going to be proportional to a prior times a likelihood. But here the likelihood is takes the form of an integral with respect to some random variable z. And it may be that this integral is intractable. We cannot compute it, or it is too expensive to evaluate. A way of approximating this integral consists of using importance sampling. So what is the idea behind importance sampling? Well, given an instrumental distribution, q indexed by x, and if you can sample some z's, which are similar to these z's, independently and identically from this distribution, and provided that this ratio here, so the likelihood on the extended space divided by your instrumental density is well defined, you can consider this estimator of this integral. okay, it is not very difficult to check that this is unbiased estimator of this integral, right? So that's important sampling. And you can think of this as being a noisy measurement of the intractable likelihood in this model, right? And the remark made by Marc Beaumont is that basically you can think of replacing this true integral with the estimator. And then you get a posterior which is of this form. So here I've done a bit more work than just plugging in this estimator in here. What I've done is that I've multiplied with the true likelihood and divided by the true likelihood and used some color, right? But in the overall, what I've done is taken the prior and multiplied it by the estimator. So why did I multiply and divide by the true likelihood? It's because here you see what you obtain is something that is proportional to the true density, right? And if you divide by this, basically this has an expectation of 1. And you can think of this red thing as being a multiplicative noise of the true density, right? So that's the framework I'm going to use. That is basically throughout the talk, whenever possible, I'm going to forget about these z's, for example, and I'm going to consider a model for the algorithms that I'm going to consider, which is going to be such that I'm going to consider noisy measurements of the density of interest, which are of this form. The true density times a multiplicative noise, which will be the noise will be positive with probability 1 and will have an expectation set to 1. So that's the framework that I'm going to consider for part of the talk, right? The noisy measurements of the density are going to be of this form, where the W's are positive with probability 1, and they have an expectation of 1. So you could replace 1 by any constant, provided that it doesn't depend on x, and you would obtain the same result. So that's not a constraint at all. Okay, it's just to set this to a constant value. And basically, it turns out that thinking of algorithms in this setup covers at least all these scenarios, which are of interest to statisticians, right? And basically what I'm going to talk about, I'm not going to talk about all these models separately whenever possible. I'm going to talk about this model for the algorithms. So how can we use these noisy measurements in Markov chain Monte Carlo algorithms, for example? So this is a repeat of what the setup is. And let's have a look first at the main workhorse of Markov chain Monte Carlo methods, the Metropolis Hastings algorithm, which will have a transition capital P. How does it work? So it's a Markov chain which is ergodic, which is designed in such a way that it leaves the distribution of interest invariant and such that it is ergodic. Given that the Markov chain has reached a state x, we use an instrumental distribution index by x, which is going to sample a possible transition for the Markov chain. But not all proposed transitions are going to be accepted, and they're only accepted with this probability, right? So this quantity is less than 1, that's a probability. And of course, what is important here is that this acceptance probability depends on the values of the density at x and y. So if you do not know, if you can't evaluate pi of x and pi of y for any value of x and y, you cannot implement this algorithm. And in what follows, I will refer to this acceptance ratio as Rxy for obvious reasons. So now let's say that we are in the scenario where this is very expensive or even impossible to evaluate. What could we do when we've got access to cheap, noisy measurements of the density? What one could do is just replace these two values with the noisy measurements, right? So this is what I'm going to consider in the next few transparencies, this algorithm where these quantities are replaced by the noisy measurements. So how does the algorithm proceed now? So the algorithm is perturbed. It has the transition probability as a tilde to reflect this. Given that the Markov chain has reached state x, we sample a potential transition. But now what we need is a measurement of the density pi of y. And I'm going to call it pi of y times u. So the noise for y is going to be called u. And then we just replace the true values with the measurements. And this is what the acceptance probability in this scenario is going to look like. And of course, if you rearrange terms, what you observe, so there should be a min here. What you observe is that this is the minimum of 1, and the acceptance ratio of the algorithm you would have liked to implement times the ratio of the perturbations of the noise. So basically what we've done by replacing these two quantities with their noisy measurements, we've perturbed the acceptance ratio by this ratio of the noises. And of course, this is not what you implement in practice, okay? This is just an abstraction of the real algorithm. It turns out that, of course, P tilde can be seen as being an approximation of the idealized algorithm, but it turns out that it is exact, right? And I'm going to explain the exactness in exact approximation. So let's consider this joint probability density here, which consists of basically x, the thing we are trying to sample, and w, which is the noise, the multiplicative noise. So now we are going to work on the joint space of x and the noise associated to the measurements of pi of x. And we are going to consider this probability density. So it's not very difficult to check that this is a probability density because we've assumed that the integral of w with respect to qx of w is 1, right? So if you integrate this, you get 1, and then you're left with a probability density pi of x, so it all integrates to 1, and because w was assumed to be positive, this is a probability density, right? So that's what I've just said. So now what we are going to consider is a metropolis Hastings algorithm, which is going to target this joint distribution, right, with this family of proposal distribution. So we use the same QXY as for the marginal algorithm, but here we introduce basically the probability distribution of the noise, right, in order to reflect the fact that we need a new measurement for pi of y. So we are going to draw a measurement. And this is what the acceptance ratio looks like. So the acceptance ratio, in this case, we are working on the joint space. So the probability, the invariant probability density is here, right? So we get this ratio, and this is the ratio of the proposal distributions. And of course, I've introduced some colors here in order to indicate that basically there are some cancellations, and you obtain this acceptance ratio. And this is precisely the algorithm which was described on the previous transparency, right? That is basically the algorithm looks like we've just plugged into the plugged approximations, noisy measurements of the densities in the marginal algorithm. But it turns out that there is an interesting interpretation of this idea in terms of this joint distribution. This is nothing but a standard metropolis Hastings algorithm which is targeting this distribution. So if this algorithm is ergodic and ends up sampling from this distribution, well, if I just ignore the noise and focus on the x's, asymptotically in the number of iterations of the MCMC, we are going to obtain samples from the distribution of pi of x. So there's no approximation in the end. We're only approximating the algorithm, but not what we wanted to do. So this looks like a miracle, but as we will see, basically there's a price to pay for doing this. Okay, and here I've copied the proof that Mark had in his paper. So you see, so this corresponds to y and x, and this is the important sampling estimator for his problem. Okay, so D is the data, and G is basically the z's in my transparency. And the way he did it, he didn't see that the central role played by the unbiasedness in the scenario. So basically, he rearranged the term. He was close to the unbiasedness. So he reintroduced this product here, the proposals, and we wrote things in this way, right? And then by hand, and then he said, well, this must be the target distribution that we are sampling from. And then he checked below here that basically marginally you recover the right marginal. So basically the unbiasedness. So he proved that basically marginally you recover the right distribution without even mentioning unbiasedness explicitly in the proof. So why is this useful? It's because this idea applies to many scenarios. And I've chosen one scenario which is, I think, quite interesting and a bit different from the standard latent variable model, although it is exactly the same thing in the end. So here we've got some data, y star, and we're considering a likelihood function of the data, which depends on the parameter L of x, which is of this form. So basically there's a function L, straight L, which we know, which is easy to evaluate, but there is a normalizing constant z here, which depends on x, okay? And the normalizing constant is of this form. And it may be that this integral is unknown, right? And that's an issue because, for example, in a Bayesian framework, if you look at a posterior distribution, well, it's going to be equal to the prior times the likelihood divided by the normalizing constant. So this normalizing constant is never an issue, right? Because it's going to cancel in the, for example, in the Metropolis-Hastings ratio. But this constant will depend when you consider the ratio of this quantity for x and for y, right? The acceptance ratio of the algorithm will depend on the ratio z of y divided by, no, z of x divided by z of y, okay? And it is unknown in many situations. So think, for example, of the Ising model. That's a situation where the partition function is difficult to evaluate, and sometimes even impossible on standard machines. Okay, so this integral is not an issue, but this integral here, and this term 1 over z, is a difficulty. Right, so to quote someone in Canada, one may use the following well-known identity. So if mu of y given x, so think of, so this should be a math frac y, okay, so it should be a y of this form. So this is a probability density indexed by x on the space of data, right? And it is a probability density, and you can consider this integral to start with. So basically you take the ratio of this instrumental density on the space of data. You divide it by the unnormalized likelihood, okay, so that's the unnormalized likelihood, and you integrate with respect to the probability density of the data given the parameter, okay, so this should be a math frac as well, okay, so I had to, you can imagine the story behind this, right? What is interesting if you do this is that, of course, this normalized density, well, is the unnormalized density divided by the normalizing constant, right? And of course, this term now cancels with this term. And we are left with the integral of, so 1 over zx comes out of the integral, and we are just left with the integral with respect to the data, and this was a probability density. So this integrates to 1, right? So basically what this identity tells us is that 1 over the partition function, the normalizing constant of the likelihood, can be thought of as being an expectation with respect to the distribution of the data of this ratio, right? So an idea may be to consider basically this extended distribution on the space of the parameter we are interested in getting sample from, and these artificial data. Okay, so y star corresponds to the true data you've observed, and y is a generic data set. And what we are going to consider is a probability density, which is going to be proportional to the prior, the unnormalized likelihood evaluated at the true data point, and then we just take this bit here and we plug it in here, right? And of course, we can evaluate this, this ratio because we've assumed that we knew how to evaluate the unnormalized density, and mu was assumed to be tractable as well. But because of this identity here, if I integrate the data, I get 1 over zx. So I integrate the data, and you see that what you obtain is basically the distribution we were interested in, right? So here we've introduced this extended distribution, and marginally when we integrate the data we get 1 over zx. So basically if you just look at x, what you're doing effectively, if you're sampling from this distribution, marginally you're sampling from the distribution you were interested in, right? Although you didn't have access to 1 over zx, which was an issue, and here it is not an issue. There's only a catch, is that of course the intractability is in here, right? But there are many scenarios where it is possible to sample exactly from this distribution. Evaluating this density point-wise may be complicated, but sampling may be easy, right? And this can be exploited in algorithms. So this idea, in fact, was introduced in a paper by Muller and co-authors before 2006, and they didn't formulate things in this way, but their idea is exactly this idea in disguise. So one question is, why is it interesting to think about these things in this way? So I'll give some examples of why it is a good idea, and in particular what I will show is that one can replace this estimator with other estimators which will have reduced variability. Okay, so just to show you that this fits in the general scenario that I mentioned earlier. So this is now our extended distribution, and there are no W's. So where is the multiplicative noise? Well, in order to get the multiplicative noise, I'm going to divide by z of x here in order to recover the true likelihood, and because I want to keep an equality or a proportional, I've divided in the denominator by z of x. So I haven't changed anything, except that now, if you look at this term, this is actually pi of x, or something that is proportional to pi of x, the distribution I was interested in. And now I've multiplied by this quantity here, and you can check, it's not very difficult, that if you integrate this ratio with respect to the distribution of the data, then you get 1, right? And for those of you who want to be a bit more precise, what I mean is that, well, you introduce a random variable w, which is this thing, and the probability that belongs to a given set is going to be the indicator that under this distribution, the ratio divided by z of x belongs to a. So there's a z, no, that's correct. I've divided by the normalizing constant here, right? So that's the connection with the scenario I've mentioned, although it was not obvious from the start. It's exactly this scenario. Okay, so we've seen that P tilde, the algorithm which uses unbiased estimators of the probability density of interest, are approximation. They look like approximation of P. They are exact in a sense that provided that the algorithm is ergodic, eventually the algorithm is going to sample from pi marginally. But of course it looks like the more W is concentrated on one, the better the approximation is going to look. Okay, but is it a good idea to look like the marginal algorithm? It turns out that there are some results which show that in fact you can never beat the marginal algorithm. Okay, but I won't dwell on this here. So it is a good idea to try to approximate the marginal algorithm. How can one approximate the noisy algorithm? Well, one may try to change W in such a way that it's going to be more and more concentrated on one in order to look like the marginal algorithm. So one simple idea is the following. Well, if for a given x we can get n measurements, and say independent for now, measurements of pi of x of this form, so they are indexed by I, then when we can suggest averaging them, right? Because we are going to reduce the variability of the approximation. So is it a good idea? I'm going to talk about this in the next transparency. Okay, and now I can refer to the distribution of this thing as Qxn. So it depends on n. There is a parameter in the distribution that has generated the noise, which is going to tune the variability of the algorithm. Okay, and one could be even more general. So before saying, telling you what one can say about these things, let's have a look at some pictures. So here is a toy example where we are trying to sample from a univariate normal distribution, 0, 1, and we are going to assume that we do not know how to evaluate this density, but we know how to evaluate this multivariate bivariate normal distribution, which turns out, which is such that it has this as a marginal, right? And what we are going to do is use importance sampling in this scenario, right? So I'm going to show you some simulations obtained using a random walk metropolis and an importance sampling estimator in order to estimate this using this joint density. And this is what one can observe after 10,000 iterations and when one uses only one sample. And of course the result doesn't look very promising. After 10,000 iterations using a metropolis algorithm, the histogram we obtain looks quite wiggly and not a very good fit of the true density. If you look at the last 1,000 iterations of the 10,000 iterations, one thing that you may observe is that the Markov chain tends to get stuck for quite long periods of time. Right, so basically the algorithm is not exploring the state space very well. So this is the price to pay for introducing the approximation. Basically the algorithm tends to get stuck. But if we increase n, so now we are going to improve our approximation by reducing the variability of the estimator of the marginal likelihood or density in this scenario. So we use 5 samples and you see that the difference is striking on the histogram. But if you look at the trace, the outcome is also quite striking. Basically, the algorithm is less stuck than it was for n equals 5. So we've increased computations by averaging more samples, but it seems that we are exploring the state space a bit better, and this is reflected in what we at least observe when we compute, when we look at the histogram of the realization of the Markov chain. And if we increase n, well, we observe even better mixing, if you look at this carefully, and we do not observe any noticeable difference on the histogram. Okay, so what is the intuition? Well, it's fairly simple, and that's quite a generic theme of this algorithm. You remember the acceptance probability of the metropolis Hastings algorithm in this scenario was of this form. It was of the form the minimum of 1, the acceptance ratio of the idealized algorithm, which we cannot implement, times this ratio, u divided by w. And of course, w may be variable. It has an expectation of 1, but from time to time, it may take very large values. Okay, so this acceptance ratio may be very small in many scenarios because the probability of drawing a y which leads to a big Rxy and a u which leads to a reasonable ratio here may be very small. So you get stuck, right? So it's maybe very difficult to escape some parts of the state space when you are unlucky and draw a very big W because of the variability. And the Markov chain becomes sticky, and this is what we've observed. So of course, it is always a good idea to try to make this ratio as close as possible to 1 in general. And one way to do it is to reduce the variability of both u and w because they will concentrate around 1. So let's have a look at some more precise measures of performance of the algorithm. So I'm going to talk about, for a generic Markov chain with transition probability capital pi, I'm going to talk about which is started at stationarity, and the transition kernel leaves mu invariant. I'm going to talk about what I will refer to as the asymptotic variance. So if you consider ergodic averages along the path of the Markov chain, that quantity is going to have a variance. And if you let the number of iterations of the algorithm go to infinity, the variance will look like a constant divided by t. So this is going to be the asymptotic constant. This is also the constant that would appear in the central limit theorem if it was to hold here. So, of course, in terms of performance, what we would like is this quantity to be as small as possible. Another quantity that I'm going to refer to is the expected acceptance probability of the Metropolis Hastings algorithm as stationarity. So if the algorithm is at stationarity, we propose a transition and we look at the expectation of the acceptance probability. And this is what one observes for the toy example that I presented earlier as a function of the number of samples used in order to improve the approximation of the true density. And this is the expected acceptance probability. And of course, what one observes is that as n increases, basically the expected acceptance probability increases. This is what we also observed on the trace. The other thing, and this increase seems to be monotonic. Another thing that one observes is that the noisy algorithm is always dominated by this red line, which is an asymptote, which corresponds to the marginal algorithm. So this was a toy example where the marginal algorithm could be implemented and the expected acceptance probability evaluated. And it seems that the marginal algorithm is always better in terms of expected acceptance probability. If we look at a more serious measure of performance, so this is the asymptotic variance, if you like, as n increases, what you observe again is a decrease of the asymptotic variance, which is a good thing, right? We want to minimize that quantity. And what we observe is that very rapidly there is an asymptote that is basically increasing n doesn't seem to improve things much. And there is a kind of asymptote, which again corresponds to the variance of the marginal algorithm, the algorithm you couldn't implement, right? So of course I'm not talking about cost here. So just in passing, there have been quite a few theoretical results in order to check whether these observations are general. And for example, for averaging, it is known that averaging is going to improve. But it's not the reducing the variance that makes it that makes the estimator lead to better algorithm. It's a stronger notion, which is the related to the convex order, and Matti will talk about this later this week. Okay, and in fact, one can show that it may be that in some scenarios you reduce the variance of your estimator, okay, but you do not improve your asymptotic variance. So it may seem to be quite counterintuitive, but there are examples which show that this is not the case. So looking at the variance of this estimator is not necessarily a good thing to do. Reducing the variance will, however, always be a consequence of a stronger way of measuring variability, which is the convex order. Okay, and in fact, there is a well-known result which says that for even exchangeable random variables, in terms of the convex order, you've got this order. If you average n+1 samples instead of n, basically you reduce variability in a stronger sense than the variance. And this can be shown to imply that the asymptotic variances are ordered in this case. That is, if you increase n, you reduce the variance. Okay? And basically the marginal algorithm is here. It's the best you can do. You can never beat the marginal algorithm. Right? So here I've talked only about one way of trying to reduce the variability of the algorithms, but I'm going to try to show you other ways which are known to some people, but not known to many people in my experience. So this is an attempt to make you realize all those other ways. So far, I've only considered a scenario where the WIs were independent. And actually, on the previous transparency, I've told you, in fact, if they are exchangeable, right? So I'm not saying much about the dependent structure in this scenario. basically you're going to improve the performance of algorithms. But in fact, you can be much more general. That is, if this is the joint distribution of all your noisy measurements, the only requirement for the algorithm to be exact is that marginally this integral is equal to 1. Okay, so they don't even need to be identically distributed. So in practice, there may be some limitations because of unknown normalizing constants, but in principle, you can consider a much more general scenario than what I've just mentioned. So one example, and it's not necessarily a good idea, but it's just to illustrate this, what you could consider is a stationary Markov chain, okay, which leaves Q of x, the distribution of the noise, invariant. Okay, so we've got a transition matrix probability T of x, which leaves this distribution invariant. We draw the first sample from the invariant, from the Q of x, the distribution, and then we iterate using T of x, right? So all the samples marginally are identically distributed, but they are dependent. So why is it interesting? Well, for example, in the doubly intractable scenario, which I described earlier, one requirement is that one has to be able to sample exactly from the distribution of the data. And this may be expensive, right? But in order to reduce variability, what one can suggest is sample where one data set, one expensive data set from the distribution of the data, and then just use possibly cheaper transition probabilities, which leave this distribution invariant in order to generate more data, which now are going to be correlated, of course. Okay, but you can use this estimator starting at 0, right? Now you can use this estimator. It's going to work. The algorithm is again exact. Okay, but this step, which was very expensive, you've done it only once, and then these steps, which are very often much cheaper, they typically give samplers and things like that, will allow you to get more samples and attempt to reduce variability by using more samples. Okay. There is an even more powerful idea, which is for reasons that I do not completely understand, which is very often overlooked, and although it tends to be it is in my view very powerful, although it comes with its own shortcomings. So it's annealing importance sampling. And what is the idea? Well, let's have a look at the doubly intractable scenario. Okay, so why is this the worst Monte Carlo method ever? Because in order to get your noisy measurements, what you basically sample is this random variable. So you sample the data set from the true distribution and you compute this ratio. So this is the instrumental distribution and this is the likelihood. So in practice you don't use the normalized likelihood, okay? But here I've renormalized in order to make sure that the expectation was 1 to be exactly in the framework the theoretical framework that I described earlier. And in practice, this ratio is going to be very variable, because in order for the ratio not to be very variable, you need to know a lot about the likelihood for this ratio to be as flat as possible. So basically, mu of x, in order for this quantity, for this estimator to work well, what you would need is this distribution to be a very good approximation of this likelihood. But very often you don't know much about this. So this estimator may not work very well. And we've seen earlier, at least through illustrations, that very variable noises is a bad thing, because the Markov chain is going to get stuck. So an idea may be to introduce an intermediate step. And the idea is the following. So you introduce an intermediate distribution, rho of x. Again, it lives on the space of the data sets. And now you sample one data set from the true likelihood, and independently you draw another data set from your instrumental distribution that you've just introduced. And for now, let's assume that they are independent, right? Why do I assume that they are independent? Because obviously, because of the independence, if I compute the expectation of this thing, well, you can separate the product because of the independence, and the expectation with respect to eta naught of this thing was obviously 1. Okay, you just cancel the ratio and then you integrate the probability distribution. And the same thing applies to the second quantity. So you can think of this as being basically the noise of a noisy measurement of the intractable likelihood. Right? And why is this, so this is just a copy of the previous transparency. Why is this interesting? Because basically, by adding this new degree of freedom, right, you may choose it in some ways that are going to be such that the variability of this quantity is going to be less than the variability of the initial estimator. Okay, so there's no theorem here or anything like that, but this is believable. And here is an example which doesn't guarantee reduced variance, but in some cases does. So if you choose the intermediate distribution, which is going to interpolate basically mu of x and the true density of the data, you can choose, for example, this probability density. If you look at what the ratio looks like, basically it's going to look like this. So basically it's like the initial ratio, but to a power less than 1. Right? So basically you're making the ratio flatter. And if you look at the exponential, so this is not a proof again, but basically you see that what you're doing by doing this, you're averaging as before, but in the exponential now, right? So you may expect that if by averaging many samples you reduce the variability of what is in the exponential by 1 over n, say, well, in total for the estimator that you're interested in, you're going to reduce the variability at a rate which is exponential of a constant divided by n, roughly. So in many situations, this is a good idea, and this is much better than using standard averages in the standard domain, right? So in fact, so there's a derivation here, which is just a way to say that in fact, of course, assuming independence between eta naught and eta 1 was maybe not a perfect thing, because in particular, if you think about the example, how do you sample from the second distribution? But it turns out that the same property holds whenever you assume that eta naught is distributed from the true density of the data set, but then eta 1 is dependent on eta naught through a Markov transition probability, which targets rho of x, the distribution you've introduced. Okay, and you can do the calculation, and basically the expectation is the same. But what is important is that the estimator is going to be of this form, right? And the same holds. So this is a practical way of introducing, using the idea that I've just described in a simple scenario earlier. You sample from the distribution of the data exactly, and then you use a sequence of non-homogeneous Markov chains in general, which are going to target your intermediate distribution, right? So now we've introduced one distribution. Well, you can introduce as many intermediate distributions as you want in between in order to interpolate these two distributions, right? And this is the general scenario. You can, for example, use this kind of interpolation of the true distribution for a sequence of temperatures. And this idea, in fact, was suggested in this scenario by Murray and co-authors. So this is the date when it was put on archive, but that's a much older idea, probably 2006, right? And the way to implement the algorithm is to introduce this sequence of Markov kernels. So we are going to use a non-homogeneous Markov chain, and each kernel indexed by t is going to target this distribution, for example, right? And everything that I've told you about the scenario where there was only one intermediate distribution is going to work, okay? Except that now the noisy measurement is going to be of this form. It's going to be a product of ratios, and the name of the game here is to make sure that these distributions are very close, so that you get something that is very flat and reduce the variance. And this can be incredibly efficient when well implemented. Okay. However, taking advantage of parallel architectures in this scenario is not obvious, okay? Because by nature, the algorithm is sequential because of the Markov chain that you're introducing. So in terms of variability, these algorithms will tend to have a high return, but they are not easy to, it's not easy to take advantage of parallel architectures in this scenario. Whereas when you just use standard averaging or naive Monte Carlo, it's very easy. You just do the same thing m times, where m is the number of processors that you're using. Okay. Another idea to improve performance is to introduce dependence. So here I'm going to talk about something rather abstract because I do not know of many algorithms which can really implement this, but I've got some ideas. So one issue with this noisy algorithm is that when W is going to be large, basically it's going to be very difficult to get a reasonable probability of escaping that state. So one possible idea would be to say, well, if W is large, I would like to favor drawing U's that are very large. Okay, so it means that I'm introducing some form of dependence. Okay, so that's going to be an idea. We want to introduce, if you like, positive dependence between W and U. And to that purpose, instead of considering just Q of X of dW and Qy of du, the noises for both X and Y, okay, what we're going to introduce is a joint distribution, and now I'm not telling you what it looks like. It's just a joint distribution which depends on X and Y, but which is such that marginally the distributions of W and U are precisely the distributions of the noises that we've introduced earlier, right? And in fact, it's not very difficult to show that if in addition we've got this symmetry property, so if you flip X and Y and A and B, you obtain the same quantity. If you do this and you consider the algorithm where basically when you're at X, you sample Y, and given Y, X, and W, you sample U from the conditional distribution of the U's given the W's, if you like. And if you use the same acceptance ratio as the acceptance ratio given here, basically the algorithm is exact in the sense that the invariant distribution remains the distribution you're interested in. So you see we are slowly here departing from the scenario where we're just approximating the density. Now it looks more like we are trying to approximate the acceptance ratio, and this is going to be the rest of the talk. So one implementation of this idea, although not many details are given in that discussion, is by Lee and Holmes. In the discussion of the PMCMC paper, basically this is discussed. I'm not saying that they checked this condition. They've implemented something and they've observed very big improvements, at least in their scenario. Okay, so now I'm going to talk about rejuvenation, because I've talked about using multiple copies in order to reduce variabilities, but in fact there's something more important when you introduce multiple copies, and I think that this is one important point which is often overlooked. Okay, so this looks intimidating, but it's actually extremely simple. So what is it that we are doing when we are averaging samples? Okay, we are targeting basically this distribution, right? So a joint distribution, pi of x, the distribution of our noises, and the average of the noises. But one interesting thing to do is to think about, is to put the sum sign in front of the everybody, right? So this is what I've done here. You just take this and you put it in front. You can do that. There's no dependence on I in here. And what is interesting here is that now this looks like a mixture. right? So this looks like the sum over a probability distribution. Now we've introduced an index k in order to reflect the fact that we are introducing a new random variable which is discrete values and takes its values between 1 and n. Okay, and this is a probability distribution. You can check it. Okay, this sums to 1. Okay, you get pi of x, and then if you integrate k, you get 1. So basically, one interesting thing here is that when you start averaging things, right, if you just put the sum sign in front, what you realize is that in fact what you're doing is that you're sampling from a mixture, right, a discrete valued, a discrete mixture. And in fact, this is an important structure, okay? So, and this is one of the other ideas that is in the PMC-MC paper, although I must say it is hidden, okay, but it is there. And now we are stepping beyond, I would say, the idea of using unbiased estimators because of that structure. So why is this interesting? Well, we know how to sample from certain quantities of mixture. So now we're going to try to sample from this distribution. We are not summing anymore. Okay, the summation is going to occur marginally, okay, because we are going to sample the case. And what we can note is that basically we can look at the distribution of k given all the other variables. And it has a very simple form. Okay, it's just basically the wk renormalized by the sum of the w's, right? So that's one first remark. The other remark is that if you look at the distribution of all the noises given k and the corresponding noise and x, basically it is of this form. It's the distribution that you've got here of this form. And in some cases you know how to sample from that distribution. And the other point is that because these are conditional distributions of this distribution, right, if you've got a sample from this distribution and you sample k given all these variables ignoring k, or you sample all the w minus k ignoring basically the existing w minus k, basically you leave the new sample is also distributed from this distribution. Okay, so basically these two updates, they leave pi tilde, the joint distribution, invariant. Okay, and this leads naturally to the idea of using Gibbs sampling, right? So in addition, so it may be that k doesn't exist, right? But of course there is this trivial decomposition of the joint distribution we are interested in terms of, well, basically the marginal. That's the pseudo-marginal distribution, okay? That was the starting point of the talk, times the conditional distribution of k given w1 up to wn. So even if you're using a standard pseudo-marginal algorithm the way I described it so far, you're targeting this distribution, but we've seen that we've got an expression, simple expression for this. So we can always sample k. We don't need it, but you can always sample it. And once you've got k, well, you can sample the w minus k's. Okay, so basically provided that you can sample from this conditional distribution, and in many situations you can resample all those w's, okay, and that's what I call the rejuvenation, right? That is, you can rejuvenate part of the noisy measurements that you've got from the previous iteration of the algorithm using this scheme. You sample k, and then from this distribution, if that is possible. Okay, and in fact you can rewrite this by combining these two steps. So basically you've got this transition probability from the noise and w, so we are looking at things marginally, and basically you can sample a k, sample from this conditional distribution, and you haven't changed the distribution of your samples provided that they were at equilibrium. So you can rejuvenate your w's. So if you've got a w that is very bad, okay, you can at least mitigate, trying to mitigate having very bad w's by changing them. Right. So particle MCMC, basically at a conceptual level, it's more or less the same, but it's much more complicated, right? And why is it complicated? Because you can write things in this way because of the sequential structure. So the noise has a very complex structure, and you can write this. Okay, it's just that it's not usable because in practice, this distribution is intractable. The distribution of the weights is intractable, so you can't use these ideas. Okay, but what is interesting is that you can expand, at least conceptually, this product, and you're back to exactly the scenario where you're averaging samples. It's just that now, in order to identify the components in your mixture, you need a very long vector because there are many, many components in this thing. Okay, and there are ways to rejuvenate, which are quite complicated and that I'm not going to describe here. But basically, the ideas of rejuvenating basically correspond to the conditional SMC. But it's much more complicated because of the very complicated dependent structure. You've got to work in a more in a bigger space in order to be able to do anything. Okay. How to choose N? Well, there's been some progress in this direction, but some people will talk about it. So I'm not going to discuss this here. I'm going to discuss only in the few minutes that are left. I'm going to talk about how to approximate the acceptance ratio directly. And I'm going to look only at a simple scenario, and I won't have time to look at the more general scenario. Okay, so far this is what we've looked at. We've basically approximated the acceptance ratio in this way, where W and U were somehow independent. We've seen that we could introduce some dependence and that it was potentially a good idea, but we would like to push this further. Okay, so can we approximate the ratio directly? Because really this is what matters. Okay, what matters is not approximating the density, but approximating the ratio. So one could think of now, because we are going to approximate the ratio, consider distributions indexed by X and Y, where we are and where we're going to be. And these distributions are going to generate multiplicative noise for the acceptance ratio. So we are going to look at this type of algorithm. But we still want to preserve the marginal invariant distribution. So this is what the algorithms may look like. So we're going from X to Y. We propose Y given X in the standard way, but now the acceptance probability is of this form, right? And what is interesting is that now the noise has disappeared from the Markov chain. Okay, we don't need the noise in the Markov chain because we are generating the noise for given X and Y. Okay, so this is more or less a standard Metropolis Hastings algorithm, except that we've got this integral. So in fact, one can show that a sufficient condition to ensure that marginally pi is invariant is to check a condition of this form. It's a kind of symmetry condition, and I won't dwell into this too much. So what is interesting is that it covers many, many scenarios of interest. So this is a toy example, although it is interesting in some respects. A distribution of this form is going to satisfy this condition, right? And you can imagine drawing the A's randomly and then considering this distribution as a second stage, a composition, then the distribution is also going to satisfy this condition. Another scenario is, well, if the distribution is a log normal distribution, then you can check that you satisfy also this reversibility condition. And in fact, it corresponds to the penalty method, right? At least the abstraction. And here is possibly the last example of the talk. Again, intractable likelihood. Well, in this paper in 2006, it was suggested to approximate the acceptance ratio in this way. So basically, you can formalize things in this way. You just multiply the acceptance ratio by this ratio of the likelihood where the data is drawn from this distribution, right? And in fact, like you can check, so of course you can check the reversibility by hand, but in fact, it falls this algorithm falls exactly in the scenario that I've mentioned earlier. Okay, you're approximating the acceptance ratio, and in particular, you're satisfying exactly this property. And you can check it in 2 lines. I won't go through the calculations here, but you can do it. And you can identify, of course, this ratio here is going to play the role of the noise perturbation for the acceptance ratio. And you can figure out what the distribution of that multiplicative noise here, right? So there's a more general scenario, but I won't dwell into it, which in fact covers another interesting scenario, but I will skip these things. Okay. So now it's more or less a conclusion. So it may not always be obvious and straightforward to estimate unbiasedly, okay? But there are general techniques in order to debias sequences of asymptotically unbiased estimators. And I refer you to this recent comprehensive review of these techniques, okay? But one point to remember is that these techniques, they come with their limitation, and that there is a trade-off between basically the quality of your sequence of estimators and computational cost. Another question is, well, ensuring exactness may be very expensive and come at the cost of variability, and variability will slow down the algorithm. So is it worth it? Well, I think there is no definite answer for this, and I guess that it depends, because, for example, it is clearly one additional thing to worry about if you don't have exactness. So, for example, let's assume that your estimators are biased, right? So you don't have 1 here. You've got a dependence on x. Well, then you've got to make sure that pi of x times the bias defines a probability distribution, okay? Because if you run an algorithm for something that is not summable, you may get something that is transient, okay? So you get a crazy algorithm. So this is an additional thing to check. You know, if you've got exactness, you don't have to worry about this kind of issues. But at the same time, in some scenarios, the gains in terms of speed of convergence of the algorithms can be quite dramatic. Okay, and there is a small example in the paper with Gareth, where we get geometric ergodicity for the biased algorithm, and we don't have geometric ergodicity for the unbiased algorithm. And this has been observed in various scenarios. Okay, and that's the conclusion. Thank you. Oops.
To avoid eating the coffee time, perhaps we can just take one very quick question. Quick question from anyone.
Yeah.
In operational research, there are techniques which are starting from almost any estimator. You can compute an unbiased estimator by random, using random series of representations. Are these techniques applicable there, or?
Yeah, so I think that the papers I was talking about here and the review by Pierre and Alex are precisely about this kind of ideas.
And is there some theory around that? I mean, you can say something about the ergodicity of these algorithms, or whether they are good or bad, or whether it's good to unbiased.
So the algorithms where you use those techniques, I don't know. No, I don't know anything. Yeah.
Okay, so let's thank Christophe again.